So now we've learned a little bit about polar and Cartesian coordinates. We know that Cartesian coordinates x, y can be converted to polar coordinates r, theta, and back using a couple different formulas. For example, we know that x is equal to r cosine theta and y is equal to r sine theta. So if you're given r and theta, you can work out x and y. Meanwhile, we know that x squared plus y squared is equal to r squared. And theta can be found using the arctangent function of the slope y over x. Our next goal will be to consider equations. And the equations might show up in polar form, and we'd like to convert them to a more convenient Cartesian form, or maybe it'll happen the other way around. So this video is giving you some examples concerning those ideas. So first I'll take you through two very simple examples, and then I'll show you a slightly more complicated example that will achieve this goal of writing polar equations in rectangular form. Suppose I have the polar equation r equals 2. It's a very simple polar equation. And of course, if r equals 2, that implies that r squared equals 4, because I can square both sides of the equation and keep it true. And of course, if r squared is equal to 4, then that means that x squared plus y squared is equal to 4. And I've achieved my goal of writing a polar equation, r equals 2, in rectangular form with x's and y's rather than r's and thetas. Suppose you had a slightly different example. Maybe you had the equation cosine of theta is equal to 6 over r. What I might try here is multiplying both sides by r. Then I'll have r times the cosine of theta is equal to 6. And we know r cosine of theta is equivalent to x. So I can substitute for x. And lo and behold, I've converted my polar equation, cosine of theta equal to 6 over r, into a very, very simple Cartesian or rectangular equation, x equals 6. In these two very simple examples, I think you see the two main strategies that you'll utilize when writing polar equations in rectangular form. On the left, we saw the strategy of squaring both sides, and on the right, we saw the strategy of multiplying both sides by r. The reason those strategies are so powerful is they're able to create the equations that we saw at the very beginning slide, that x squared plus y squared equals r squared, and the r cosine theta equals x, and the r sine theta equals y. So you're able to substitute using those formulas, so to speak. Let's look at one last example. This example, you'll see, utilizes both of those strategies in the same problem. So in this problem, we have r is equal to 3 divided by 1 minus 2 cosine of theta. So to start out, what I'll do is I'll multiply both sides by 1 minus 2 cosine theta, and I'll have r times the quantity 1 minus 2 cosine theta, and that'll be equal to 3. Naturally, I'll distribute the r, so I'll have r minus 2r cosine theta equals 3. And of course, it's sort of natural at this point to say that must be the same as r minus 2x equal to 3, because I see an opportunity to sub in x in place of an r cosine theta. Of course, at this stage, I am not in rectangular form. I did sub out an r and a theta for x, but I still have an r remaining in my equation. My equation is not in rectangular form until I only have x's and y's. But I do notice that I could rewrite this equation as r equals 2x plus 3. And then I could try that strategy of squaring both sides. So when I square both sides, of course, I get r squared equals the quantity 2x plus 3 squared. And r squared, of course, is x squared plus y squared. And when I square the binomial on the right-hand side, I'll get 4x squared plus 12x's plus 9. And now maybe I'll put everything on the right-hand side of the equation, and it'll say 3x squared minus y squared plus 12x plus 9. And you could write that in some different forms if you like. And if you're familiar with graphing hyperbolas at all, you might recognize that that's a hyperbola because of the different signs on the coefficient of the x squared and the y squared term. But Either way, that is an example where you had a more complicated polar equation and you were able to write it into rectangular form.